Hey folks, welcome back for another episode of Code Club. In this episode, we will be doing a recreation, as you could kind of see in that screenshot that I had to kind of introduce the live stream here. The idea is that, let me pull it up here, that we are going to start with a stacked bar plot like this that was recently published in the journal Nature Microbiology. This is from a microbiome study, which is near and dear to my heart, the microbiome research, not the study necessarily. But something that was unique about this study was that they had a before sample and an after sample from each of 8 mice that underwent 4 different experimental conditions. Again, what those conditions are isn't super relevant. There's a control. There's a set of mice that received a carbose, a set that received antibiotics, and then a group that received both antibiotics and a carbose. And so as you can see in this version of the plot, they have a before and an after. So the before was from like day 21 of their experiment, and after was from day 28. And so then they are trying to compare. And as I talked about in a critique video that I posted yesterday, this is just not working, right? It's really hard to compare this column to this column, or this column to this column, without even getting into the fact that there are 21 different colors in their legend. And I have this blown up pretty large, but in the paper, it was taking up a space of about, I think, 5 inches wide by 2 inches tall. So it's really small. And what I would like to do in this episode is try to refactor it. And so this is a little bit of what I have in mind based on some practicing I had done, where we can convert the stacked bar plot into what I'm calling a slope plot. And I would then color the slope by whether or not it was significant. So if it's gray, not significant. If it's red, it was a significant increase between the before and after for that condition. If it's blue, then it's a significant decrease, right? And then we have these bars over the top to say, like in this case for the Bacteroideaceae, that the increase for the antibiotics plus a carbose was greater than the increase or the change for any of the other conditions. Okay, so I am not going to deny that this is a complicated experimental design, but I think the stacked bar plot leaves a lot to be desired, and want to take a swing at trying this. I am drawn to stacked bar plots because I'm of the opinion that there is really no good situation, or the number of situations is so limited where a stacked bar plot works. And so I am committed to trying to find ways to refactor stacked bar plots into something that's easier to interpret. And I think this in the lower right corner, what we're going to do today, is far easier to interpret than what they did in the original. All right, so as you are logging in and getting settled this morning, I would love it if you would tell us who you are and where you're coming from. We've got John from Barrington, Saeed from Somalia, Mike from the UK, some of our regulars. Great to have you joining. Thank you. Let me see. Okay, so as we get going, as always, I want to call your attention to the Riffomonas website, where you can join a mailing list. I put out a newsletter once a week about some aspect of data visualization. Normally it's about talking about data visualizations at a very high level, at like a 30,000 foot view. This was panel D from the same figure in that paper. I actually will have a recreation video where I take panel D here and convert it into this, that will be coming out either tomorrow, on Thursday, or on Friday. There will also be another another recreation video where I look at panel E. And so what are these panels? Well, again, panel D is that plot I just showed you from the newsletter. Panel E is an ordination, and then panel F is what we're going to be working on today. Needless to say, I was not a fan of this set of panels or the figures in general that were published in this paper. And so this comes from a paper titled "A Carbose Redirects Gut Microbiome Utilization of Dietary Carbohydrates to Suppress Anaphylaxis in Mice." And like I said, this is a paper published in Nature Microbiology coming out of lab in Japan. It is open access, so I'll go ahead and throw this into the chat. And if you want to check out the article, you can get it. You can check it out for free. They have also made their source data publicly accessible. Let me go ahead and also put in the newsletter that talks about this visualization. And then I'll also go ahead and show you all the critique video. I posted the critique video on Monday, which in the US was a national holiday, Memorial Day. And so I don't know if maybe people didn't see it. I know many of the viewership, especially of these live streams, are international. And so again, if you haven't seen that, would encourage you to check it out. Feel free to leave a comment. Let me know what you think about those visualizations. And again, what we're going to focus on is panel F. So we've got Mark from Melbourne, welcome. We've got Mr. Jaggerjag from Spain, although he is, or they are, I also miss him, if he's Mr., is on a trip to Berlin. All right. Ich bin ein Berliner. Was that a Kennedy quote? Anyway, my last name is German, but that doesn't mean I know any German at all. So anyway, as I said, we are going to use the data that they provide to recreate panel F. And if you haven't watched my live streams before, well, to get the data or to see if there's data, the bottom corner of these figures, oftentimes, not always, there will be a link for source data. And so if you then check out source data, you'll see source data figure 3, and that you can download this as a Microsoft Excel workbook. And so you can download it, you can copy the address, whatever you want to do to get that data. I am going to be working here in RStudio, and I have this R script already created. If you want to get a copy of the code that I'm generating today, as well as the links that I've already thrown up, go down below to the description for this episode after I'm done live streaming it, and you'll get the code that we've got today. I've already kind of populated some code in here to get the tidyverse and readxl loaded to download that workbook. And then because we're going to have to clean up the workbook a little bit, I've put in these long names so that people don't have to watch me typos, typing, or dealing with copying and pasting and reformatting things. So let's leave that in there. And then I also have this ggSave statement, which I'll go ahead and call this bar plot. Or no, I'll call it figure 3E. I think that's what we're doing here, right? Just to double check, figure 3F, not E. All right, figure 3F refactor. All right, and then the dimensions I'm putting in here are a width of 5 and a height of 2. That this figure in the original is taking up, I would say, about 2/3 of the width of a page, right? And so then looking at this aspect ratio, it's like 5:2. That's kind of the way it works out. I don't think that it's using a full page, so it could certainly be taller. There's also panels down here that are taller than they probably need to be. So I suspect before it's all said and done, we'll make our own version of panel F a little bit taller than what they had. All right. So I would love it if, as we go through, wonderful. We have Sid from Sweden, Mark correcting my Deutsch, and James from Toronto, and then Sid, yeah, tell me more about pastries. So feel free to leave comments or leave suggestions or questions as I go through this. I would love to clarify that. One of the benefits of doing a live stream is that I get this type of interaction with you, which I really love. And I think it's great that we have people from around the world talking about code together as we go through it and getting to spend some time here this morning. My goal is for this to go 2 hours. It's a little bit complicated, so it might go longer than 2 hours. So bear with me if I'm going a little bit fast, but feel free to ask questions. And so also, if you want to ask questions of me directly about your own work, then again, down below in the description, there'll be a link for a sign up where you can go and you can sign up for a 30-minute complimentary meeting where I can learn about your needs in terms of data visualization, reproducible data analysis, and we can perhaps figure out a way that I can help you with some coaching or consultation for your own research. That's something that I would love to do. And it's great to do this with figures that are already published, but it would be even better to do it on things before they're published so that you're putting out the most clear and best representation of the work that you are doing. Okay, so, all right, let's get going. And I'll go ahead and load my different libraries and get those going. And so again, this download file downloads figure3.xlsx. And if we open that up, let me get rid of my face here. This is figure 3F, which is a tab from this workbook. And this is not tidy at all. They have some other tabs in here that are, I would say, tidy-ish. Like this is for E, which is that ordination where they've got basically all the information in separate columns. Although this is like merged cells. Don't merge cells, okay? Don't merge cells. They've got some merged cells in here as well. And so we need to get this into R and clean it up. So one assumption that I'm making in this series of videos is that everything in like the first column is from the first mouse, from like mouse 1 and then mouse 2 and so forth, right? And so that like this column goes with this column, that these 4 relative abundances go with these 4 relative abundances, right? It would have been nice if they could have like given some index or indication of like the mouse ID, but regardless, I'm not trying to like redo their analysis. I'm trying to think about how we could perhaps refactor the visualization. And so again, I'm not totally trying to reproduce their work, but this will get us going. All right, so coming back here, let's go ahead and we will read that in with readxl, and we'll do fig3.xlsx. And if we read that in, we're actually going to get the first page, which is not what I want. That's for, I think, panel B. But we'll go ahead and do sheet equals fig.3f. And so that gets us this figure. And we see a bunch of NA values because it's not really sure what to do with all those merged cells. And so I'm going to give a range. And I think what I'll do is I'll start here at C4. So we can do range equals C4 and the colon. And then we'll come to the bottom right column, which is FO11. So FO11. And that then gets us this. And it's not reading in the column names, right? Because I skipped. I started on row 4 rather than on row 3. If I had done 3, then we would get like Acromantia and basically the various names. But in between, for those 8 mice, we would get blanks, which is not what we want, okay? So let's put this back to 4. And then we're going to give it a call names argument. And I'm going to call it call names, okay? And so to make call names, maybe I'll cut this and paste this down below taxa. Again, looking at the Excel workbook, we have the different families of bacteria, and that, again, there are going to be, let me just go back to the beginning. I'm pretty sure it's 8, right? That there are 8 cells there, okay? And so what we can do is to take, let's go ahead and do, let's do replicate, right? And, or maybe we'll do a mouse, we'll call it mouse. And we'll do 1 to 8, and we'll repeat that 21 times, or length taxa times, okay? And what that gets us then is, if I look at mouse, is 1 through 8, 21 times. And so then what I can do would be to do call names, and we'll do paste, and we'll do taxa, comma, mouse. And let's go ahead and do sep equals underscore in quotes. And so now if I look at call names, I get, my 21 taxa, not exactly what I want. All right. I need to, right. It's repeating my 21 taxa 8 times effectively, okay? Which is funky, right? So that's always good to check out our work. Okay. So what we want to do instead then would be, we want to rep the taxa each 8 times. And so then if I look at this, this is going to give me each of the 21 taxa repeated 8 times. And then when I merge that with the mouse ID, now I can see this is the output I was hoping for, where again I have like Acromantia 1 through 8, Atopiaceae 1 through 8, Bacteroideaceae 1 through 8. Okay. So we now have our column names, and let's go ahead then, and well, that's here. And so then we read that in, and it is complaining that sheet 5 has 169 columns, but call names has 168. And that is, yes, because there's a column here that I missed, right? Okay, so we need to go ahead and add that, and I'm going to call that treatment. So maybe we'll do C treatment on that paste. And now, why didn't that work? Oh, and I think I forgot a closing parenthesis here. Okay, there we go. Now we've got it to run with no errors. We have the treatment column, and then we have 168 columns, which is 21 times 8 is 168, right? So then we have 8 columns for each of the different mice and the bacterial family and its relative abundance. We need one more column added, which is the time, right? So again, if you think about this column, they're calling it treatment, which isn't right. I mean, that's not what I would call it, but there's a before and there's an after. And so I'm going to call that time. And so right in here, I'll go ahead and do a mutate, and I'll do time, and then we'll do rep, and I'll do before and after, and then we're going to rep each of those 4 times. And so, oh, come on. Oh, and this should be, sorry. I'm slowly getting going here. We're going to repeat each of those 4 times. Sorry for that. And that then threw that at the end. And I think I maybe showed this before, but maybe not. We'll go ahead and do it dot before equals everything. And so now what you can see is that we have that first column, time, and then treatment, and then those bacterial family names. Okay. Yes. So, yep. Thanks, Mark. We've got Francisco from Colombia, Folosia from Brazil. Welcome. And good. So now we've got this. What we'd like to do is go ahead and make it tidy. And so what I'd like to have then is a column for the time, the treatment, the family, the animal, and then the relative abundance. And so I'm going to make it longer, pivot longer, and then we're going to separate out the family mouse, or what's currently the column name, right? So we'll go ahead and pipe this and do pivot longer, and then we'll do calls equals everything. So we'll do minus C, but the time and the treatment. And so again, now we should get, when we do this, we're going to get 4 columns. And so we'll do names 2 equals family mouse, and then values 2 equals rel abund. And let's go ahead and put this on separate lines. Sure enough, we now have our 4 columns with family mouse and rel abund. And then I'm going to do a separate wider delim. And so that's going to separate the family mouse column. And we're going to use as a delim our underscore, and our names are going to go to family and mouse. And so now what we can see is that we have 5 columns, right? Time, treatment, family, mouse, rel abund. Awesome, right? And so let's go ahead and maybe put some of this on a separate line, and we'll then pivot this. And yeah, now we're ready to like think about plotting, which is always fun. All right, let's take a breather here. Okay. So let's think about like ggplot AES. On the x-axis, we could think about putting the time, and or let's put treatment maybe, and then on the y we could think about putting the rel abund, and we could do like color equals treatment, and we could then do group equals mouse. So what this is going to do is on the x-axis, it'll put the treatment. So like the control, the ACR, the ABX plus ACR, right? Those four different things. And we will then, on the y-axis, put the relative abundance. Then we will color by whether it's before or after. And the grouping is going to be by mouse. And so I don't know if it might be premature to do geom line. But we're also going to want to facet, I think, by the family. So facet wrap. I know sometimes I recreate other people's visualizations. I'm not going to do that here because I don't see the need. So we'll facet wrap family. So basically we'll make 21 plots for each of the different families that we have in the data set. And so let me go ahead and open that up. And we see not much. Oh, that's pretty, it's pretty hard to see anything, right? All right, let's go ahead and open this up to say 4 inches high. And there we go. Now we have something we can kind of look at. And maybe for now, I'll go ahead and get rid of the original because I don't think that's going to be much of a template for what we're doing here. And so what we can see maybe is across the x-axis, we have those 4 treatment groups. The y is the relative abundance. We have the 21 different taxa. And then we have 4 colors for the different treatment groups. And it is connecting the data, so like mouse 1 in the control group to mouse 1 in the antibiotics, mouse 1 in the carbos, and so forth, right? So it's basically drawing a line across all of those. So if instead of group mouse, I did group like paste mouse, comma, treatment rather, I need another parenthesis. This then is getting us not what we want either. It's drawing a line. Oh, I did treatment, color by treatment. Okay, let's do color by time and see what that gets us. All right. Well, that's not much better because basically we have all our points are on a vertical, right? So if I change this geom line to geom point, there we go. You can see that the before and the after points are basically in the same column. So if instead I did like position equals position, position dodge, and I think I need to indicate the width. So if we do like width equals 0.3, there's a bit of a dodge going on, but we can't really see it. So if I take that up to like 0.5, yeah, it's dodging it within my group, right? So let's go ahead and go back to geom line. And here we're not gaining on it, right? All right, so maybe what I will do is instead of trying to do all the things all at once, I'm gonna filter the data down to only look at one taxa, right? So let's do filter family equals, and oh, let me come back up here, and I'm going to grab factoid ACA and run that through. And it's upset because I always do that. I only put one equal sign instead of two. And so now what we have is the antibiotics, the 4 treatment groups, and then we have our before and after. And so it's always nice to like shoot for the moon and do everything all at once, but that usually doesn't work. So I find that by filtering down to like one example, we can get that to work and then bring in everything else and then facet across all those other things, right? So let's go ahead and, so X is the treatment, color being the time. Again, let's go ahead and remove that color time. And let's see, if we do that, that again gets us a vertical line. And if we add back in that position dodge, what this is doing is this is dodging my lines, which is not what I want, right? And if I were to perhaps do like geom path, again, we get the same thing, right? And so what we're going to need to do in this situation is to roll our own position dodge, I think, right? And so there's other ways to do this. And again, in tomorrow's video that I'll be posting, I'll show you 2 different ways that you can make a slope plot. I'm going to take the first way of those approaches, which is basically to make my own dodge. So let's come back up here. And after this filter, or maybe before the filter, again, what we have here is this readxl. And what I'd like is to make my treatment an x-axis position, right? And so it's doing that automatically. It's effectively using like scale x discrete. And so what I want to do is convert treatment into a factor, and then I can use @numeric on the factor to get the index, the x position of that factor. So let's go ahead and do mutate, and we'll then do treatment. Oh, sorry, treatment equals factor on treatment. And we'll then do levels, and we'll do CTRL, ACR, ABX, ABX plus ACR. And we'll put this on a separate line and pipe that. And so, again, if we run this, like so, we're now going to see that instead of being a character up here, it's now a factor, right? And that's good too, because then that will, if I kind of fold that in with the rest of this pipeline, I'll now see that I've got things in the order I desire, right? This is the order that they were using throughout the paper. So that's cool. The other benefit then is that also within this mutate statement, what I could do would be like x equals as.numeric on treatment. All right. And so then what we'll get, again, if I run to that point, is a column for the x position. And if I take like dot last value, I'll do print, n equals inf to see, oh, that's going to show me everything. I don't want that. Let's do tail. And this should then, oh, come on. That then shows me an x position of 4, right? Okay, so that's going to be like the x position. But as I said, I can add a dodging to this, right? And so let's go ahead and then do x equals if else, and I'll do time equals before. Then I'm going to do x minus a dodge. And if it's not before, we'll then do x plus a dodge, okay? And so then I need to add a dodge value. And let's do 0.2 as a starting place. And again, that doesn't change much. But if I, again, look at these first lines, let's go ahead and add in that factoid ACA. Then what I see already in here for my x is that the control is in position 1, right? And that I'm going to have x starting at 0.8 for the before and 1.8 for the ACR for the before, right? So that's going to be like 0.2 before 1 or 2. So again, if I kind of recycle back through this and did like filter treatment equals CTRL, then what I see is I've got 0.8 and then 1.2. And so that's going to be my x-axis position, okay? So now what I can do down here in ggplot is I can do x equals x, and let's see what this gets us. Oh, it's upset because I forgot to turn off that pipe. And so there we go. We now have these various slopes, these various lines for the 4 different experimental conditions. Yeah, last value is pretty awesome. I always get nervous though when I use it, because like you have that one chance to use it right and to get the thing you want, because when you run it, there's a new last value, right? So anyway, it is a great tool. So now we have our slopes, right? And so again, this is the control. This is the ACR, the acarbose, the antibiotics, ABX, and then the ABX plus ACR. And so I think this already shows something better than the stacked bar plot, but we still have a long ways to go to make this look nice. So I think we're in good shape now that we've got that geome line, and I'm going to go ahead and turn off that filter. And so now what we have here are, again, the 21 different slope plots, or 21 different families of bacteria, right? And we've got slope, right? We can see like the Bacteroideaceae clearly increasing in that 4th group. But like I said, we want to make this look better. One thing I would really like to do is get this down to 20, 20 different families. And I think what I'm going to do is probably drop the others category, because that's not really a category. If I knew more about the study and what the researchers were interested in, I would probably come up with other filters to remove things, right? So like this Oscillosporiaceae doesn't appear to be doing a whole lot. This Apotopaceae, right, isn't doing a lot. This Desulfovibrio, whatever, this one over here isn't doing a whole lot, right? So you could probably simplify this a lot more by removing things that are really rare and probably aren't, as we might assume, not as big of players. The other group in here that annoys me, frankly, is uncultured. Like, that's not a thing. That's not a family. There are many families that are actually uncultured. So I think they did something weird when they're making their plot. Like they, I don't know, removed anything after a space or something like that. So I'll just, whatever. Well, again, we're doing a demonstration here, and what I'll probably end up doing is removing others. But before we do that, let's go ahead and maybe pause on the data visualization and turn towards the statistical analysis, if we could do that, okay? And that's because, as I showed you in kind of the example of kind of where I want to go, is that there's 2 layers of change here that we might be looking at, right? Where we could have things changing between day 21 and 28 between the before and the after. But also like the amount of change might be different, right? So like for the Enterobacteriaceae, is this change here different than this change here, right? I'm pretty sure these are all different, but yeah. Someone says you could also give rows and columns to remove blank plots like 3x7 or 7x3. Yeah, so before I move on to that, let's go ahead and I could do like n col equals 7. And we could get something like that, right? And so that's not horrible, right? So that's a good idea. So let's hold on to that for right now. Again, if this were my study, I would be looking for ways to pull things out. And part of that might be by finding things that aren't significant, right? So like if none of these here for, I don't know what this is, if none of these are significant, then I'd throw them out. I'd remove them, right? Because there's no need to include them. So that's I think, good reason also to go and look at the statistical analysis, okay? Yeah, so James says one thing to keep in mind when considering removing things is that aren't doing anything. Sometimes negative info is also very valuable. That's correct. And so again, that's where I don't have like insider knowledge of really what they're trying to say in this study, because I could imagine a situation where, I don't know, say this is, it's not, but imagine it's like lacnospiraceae, right? Or maybe it's actually lactobacilliospiraceae. Like you might say, wow, I'd really expect like the lactobacilliaceae to be doing something. But if they don't, that's interesting, right? So again, that's where having some like insider knowledge of the problem, of the study, of like the biology that's already known is really important. Because if other people had found that, you know, this group was really important and we find that it's nothing, that's important to know. So great, good point, James. Thank you. All right. So I am going to go ahead and I think break this apart. And I'm going to do it like right here. And I'm going to call this D for data. And so then we're going to need to do a D pipe into here with a mutate on all this. And then let's make sure this works still. And we're good. Okay. And so again, we have D, which is this data frame that has the time, the treatment, the family, the mouse, and the relative abundance. And so as I said, there's two questions I'm interested in. So for each family, for each treatment, is the change in relative abundance between the before and the after significant, right? So that's question one. Question two then is, does the amount of change between before and after change within or vary within a bacterial family across the 4 treatment groups, okay? Because the pairwise comparison I'm going to use to color the lines, and then across the treatment groups, I'm going to use to kind of draw those bars to indicate a difference in amount of change, okay? I am not a statistician, so before you go off and do any of your own statistical work, talk to a statistician. The data we're working with is not normally distributed, and so I'm going to be using non-parametric tests. Things like relative abundances are not normally distributed. They have a lot of zeros in them, and so I use like the Wilcoxon test or the Kruskal-Wallis test to do a lot of my analyses. So again, depending on your application, you do you. So let's look at the pairwise first. So we'll do pairwise comparisons. And so we'll take D. And again, I want to look within each treatment and family. So we'll do nest data equals everything but treatment and family. And this then gets us 84 tables where we've got data frame with 16 rows and 3 columns. And those 3 columns are going to be the time, the family, or the time, the mouse, and the relative abundance. And actually, as I think about this, we're going to want to do a paired analysis. And so maybe I want to do something before this, that I need to get the before and after to be separate columns for this analysis. So let's go ahead and do pivot wider, and we'll do names from equals time, values from equals rel abund. And so again, that's going to give us before and after. And so then we can pipe this into nest, removing out the treatment and the family. And that then gets us basically these 84 rows, so 21 by 4. And then we're going to have 8 by 3 data frames. Then what we'll do is another mutate. And whenever I run a statistical test, I like to name the column test. I don't know why, because it's a test. That's why. And we'll do map. And so we're going to run a function over each value in data separate from all the others. Okay. And so we'll give that data. And then I'll do tilde Wilcox test. And we're going to do $x $sign before. and then $x $after. And so the $x is referring to this. So data is actually $x. That's the argument that it occupies, whereas I think this is $f, okay? Normally, I don't use the arguments, but in this case, it might be helpful to you to have that $x. And again, because the data are paired, I need to do paired equals true. And so now when we run that, we find we get a test column that is a list, kind of like data was when we nested it. And the type of data in there isn't a tibble like we saw under data, but it's htest. And so that's a hypothesis test. And so to convert that to a tibble, there's a great package that comes with the tidyverse called broom. Okay. And so within broom, they have a function called tidy. So let's, within that pipeline, after the Wilcox test, I'll do tidy. And so now what we can see is that that test column turns into a tibble with 1 row and 4 columns. And so now what I can do would be like an unnest on test. Okay. We've got Abdul joining in from Kabul, Afghanistan. Welcome. Great to have you. And happy holiday. It's Eid, I know. So welcome. And so what we see in that output is we've got the treatment, the family, we have the test statistic, the statistic value, right? And then our p-value. And so we see like p.109, 0.0156, right? And that it tells us about the method and the alternative. And yeah, okay, so let's go ahead and clean this up a little bit. So we'll do select, treatment, family, p-value. And one thing that I don't get from the statistic or the p-value is the direction, right? And so what I'd like to do is create another column that is going to tell me the difference between the before and the after, okay? And so I think what I'll do in here then will be a, yeah, okay, I'm thinking. Let's do diff, and here I will do map, again, .x on data, or .x equals data, right? And then I'm going to do median, and we'll do .x $, before minus $x $after. And so this should give me a column called diff that's going to return the median difference between the before and the after. Okay, and it's saying object.x not found. Why? Maybe I forgot the tilde on that median. Okay. I'm also not going to see anything when I run this because I've got that select statement. So, okay, let's turn that off for now. And so now what I see is that diff is coming up as a list of doubles. And what I could do would be like map DBL. And that way then we're going to return the value as being negative or positive, right? So now we have the actual value. And so if I go ahead and add that, I'll do diff. And then, oh, I forgot to take out that comment. Okay, there we go. So now we have, for each treatment, each family, we have the p-value and the difference between the before and the after. And I'm thinking that this is the wrong direction, okay? So if I look back here, acromantia is the first one, right? And so, well, that's probably not a good one to look at. Oh, let's see. Well, the controls don't change much, right? So let's do last value, print or filter, treatment equals ACR. And like that, Erysipetraceae seems to go up by like 10 percentage points with the ACR. And of course, I can't see anything. So I think that's this. And those are actually going down, right? So I think I want to flip the direction, right? To do after minus before, right? So if If it's lower after than before, then we're going to get a negative value, which makes sense. Okay, cool. So we now have this, but I haven't corrected for multiple comparisons, right? So within each family, or within each treatment, I'll think, within each treatment, we're going to have 21 comparisons, right? And so again, this is where like talking to a statistician about how to do the multiple comparisons would be pretty valuable. But we could do mutate on p.value equals p.adjust on p.value. And I'm going to do method equals bh for the Benjamin E. Hochberg. And so then this corrects for those multiple comparisons. But I want to do it by treatment, right? It might not actually matter how we do it. But if we then do filter p.value less than 0.05, we see that we've got 45 differences that are statistically significant, that are less than 0.05, right? And so I wonder, like I said, if I take off that that by treatment, again, that was 45. This gets us 47, which is weird that we get more that way. But anyway, I think it makes sense to do it by treatment. And so I'm going to roll with that. Where again, we have 45 taxa that are significantly different between the before and the after. And we also have that difference. Okay, so I'm going to do this now. So what we'll do will be to do a mutate, and I'm going to create a column that I'll call color, and I'll do if else, and maybe let's do case when. Okay, case when p.value less than 0.05 and diff less than 0. Then we need the tilde, and I'm going to put in blue. I want it to be blue to indicate dropping, right? If I've got p.value less than 0.05 and the diff is greater than 0, then I want it to be red, okay? Otherwise, I want it to be gray, okay? So again, if it's significant and it's a negative, it's a drop in relative abundance, I want it to be blue. If it's significant and if the difference is greater than 0, it's increasing, then I want it to be red. Otherwise, I'm going to have it be gray, okay? Thank you, Patricio. I don't know about being the best. Am I considering Julia or no? Maybe someday. I really like R, and I know R really well. I know there are things that people like about other languages, and there are problems with R. I know those problems, right? At the same time, like, I feel like I can do everything I need to do, or I can do everything I'd want to do in R. And perhaps there's friction along the way, but I know how to deal with that, right? Like, okay, that's a pain, but I can get over that, right? The other thing I tell people when picking a language is to think about the community around you, right? Like nobody, I don't know anybody at the University of Michigan where I work who knows Julia, okay? I know people who know Python. I know a lot of people who use R. And so it makes sense for me to use R because if I have problems, I can ask those people for help with R, right? Maybe someday as Julia gets more popular. But for now, I'm happy to continue using R. So that's my thought anyway, and what I suggest to people. All right. So again, we now have these colors, right? We've got the treatment, the family, the p-value, the diff, and the color. And just kind of doing a spot check, right? Like these are all p-values larger than 0.05, and we get gray. If I do a tail on this, here we get some blues and reds. So again, these are both p-values less than 0.05. The positive one is red, the negative one is blue, okay? And then the rest of these check out. Okay, so I think what I'm gonna do is I really only am interested in the treatment, the family, and the color. So I had a select back here. I'm gonna go ahead and grab that and bring that down here. And I'm going to get treatment, family, and color. Okay. Oh. There we go. And so now we have our treatment, our family, and our color. And what I want to do is join this in with D so that I can use the color column to color my lines. So let's go here and call this P. Not very original, I know. And then I'll do an inner join with P. And so when I run inner join, I can do this, right? But to me, I don't know, it feels better to know where the data is coming in that's getting joined to P, okay? I don't know. And then we'll do by, and we'll do treatment and family. And if we look at this, we now see that we've got time, treatment, family, mouse, relabund, and the color, right? And so I can feed this in the rest of the way. And previously I had color equals time, and I was kind of fumbling through things earlier. Here I'm going to do color equals color. And to get the color that's actually in the color column, I can come down here and I can do scale color identity, right? And so scale color identity is going to use the value in the column that I'm mapping to the color aesthetic. And so that then gives me my red and blue lines. And as if, my earlier questioning if I picked the right direction of the arrow, so to speak, of the difference, like things going up are red, things going down are blue. That's fantastic. And yeah, I'm pretty happy with that. One thing that I am noticing is that the control, which is this position 1, is gray in every condition, okay? As you'd expect, like really nothing happened to those mice except that 7 days went by. And so I think what I'm gonna do is I'm gonna go ahead and for this case, I'm gonna remove the control, and that'll give me a bit more room in the x-axis to see differences between my different treatment groups. So to do that, maybe where? I think I'm going to do that back on D. And so I think what I'll do is filter treatment not equal CTRL. And then rerunning that, I now see that I have a bit more room from left to right. So in the caption for this figure, I would need to say, the colored lines, the non-gray lines, were significantly different from 0. And that red is an increase and blue is a decrease, right? I like having the color because, again, that signifies significance. And then, I don't know, we think of red as being hot and going up, and blue as being cold and going down, and gray as being neutral. And so that's kind of why I picked those colors. You could certainly pick other colors as well. Cool. All right. So the next thing I want to think about is thinking about that change in the difference, right? So like we have, I think this is Akkermansia. We have 3 declines for the 3 non-control groups. Are those all the same, right? Is there a difference in the median decline or decrease in relative abundance of the Akkermansia? Similar for these over here, which I think are Enterobacteriaceae. Are those going up at the same rate, right? Or is there a difference? So I'm going to come back up here. And again, I think what I will do is I'm going to go ahead and copy these first couple of lines. And here we'll look at difference of differences. And again, just to remind ourselves, maybe I don't need the nest just yet. We have this, right? We have the treatment, the family, the mouse, the before, the after. But what I'm interested in is the difference. And so I'll go ahead and pivot this to a mutate, and I'll call it diff, and we'll do after minus before, right? And that's what we had used up here. And so then that gets us this column with the diff with the before and the after. And so now, again, to kind of keep things a little bit simple, let's go ahead and do select, treatment, family, and diff. Okay. And so now what we've got are the differences for each mouse within each treatment and each family. And what we can then do is this nest, right? So we're going to nest by what? By family, right? Because I want to look across the treatments to see within a family, is there a difference between the 4 treatments, right? Like the control, the ABX, the ACR, the ABX plus the ACR. And again, I'm not totally concerned with visualizing the controls, but I'll leave that in here for this analysis. So now what we'll do is another mutate. And again, we're going to use map. So I'll do test equals map on data. And again, that's that .x slot. And we have what? We have 4 treatment groups, right? We have, as we've discussed. So there's a Kruskal test, which is a non-parametric version of ANOVA. And so here what I could do would be like .x $diff, and then G is the grouping, and that is going to be .x $treatment. And so that works. Again, we've got that H test, but as we saw before, we could pipe that to a tidy, and then that gets us a tibble, and then I could also then do unnest test. And so then this gives me basically the p-values saying, is there a significant difference? So across those 4 groups, is there one group that's significantly different from another group, right? And so like what it's saying here is that like the Akkermansia have a p-value larger than 0.05. And we could also go ahead and do mutate p.value equals p.adjust on p.value method equals bh, right? And so then what could we do? We could go ahead then and do like a filter p. I'm going to do greater than 0.05 to see like what's not significant. P.value. All right. So there's 4 groups that have non-significant p-values. And that's interesting. Like those are 4 pretty commonly observed taxa. And so, yeah, okay. Let's go ahead and leave that. And I'm going to call this PKW or I'll call it P Kruskal. I was thinking KW because it's a Kruskal-Wallis test, but let's go ahead and call that P Kruskal. And so that's cool. And then so if it's significant at the experiment level, so within a family, then I feel safe doing the pairwise comparisons. So let's go ahead and clean this up a bit. So we'll do select family data P Kruskal, right? And now what I want to do is another nest, right? Or I've already nested it. So I want to do another map, right? So we'll do mutate test equals map on data. And now we'll do pairwise Wilcox test, okay? And we're going to do basically the same thing that we did up here on line 56, which is like .x $diff and then .x $treatment. And then we can also give a method. So we'll do p.adj method, and I'll do bh for Benjamin Hochberg. That runs without any problems. We've got Teresa from Portugal. Glad to have you. Don't worry about being late. And we can, again, tidy this with broom. So we'll do tidy, turning that into a tibble. So this has 3 rows because it's going to have 3 comparisons. And yeah, so it went ahead and removed the control. I think maybe I don't want to remove the control back up here. I'm gonna leave that. I feel like I should include the control because that was one of the comparisons that was used. So let's see, what do we have here? So now we have 6 by 3, because if you have 4 groups, that's 4 by 3 divided by 2, that's 6, right? So we've got 6 rows and 3 columns. And now what I could do would be like an unnest on test. And what I see is I've got P cross skull, group 1, group 2, and the p-value, okay? And ultimately, we're not going to be interested in the CTRL because we're not going to show that. And we've got those p-values. Okay, so let's go ahead then and select family p dot cross skull, group 1, group 2, and then I'm going to do pw for pairwise equals p dot value. Okay, cool. And then I will call this, well, I call that pairwise. I'm going to call this DD for difference of differences. All right, so we now have our statistics. So let's look at DD real quick. And if I do DD filter p.pw less than 0.05, I can see like for Acromantia. So before Acromantia wasn't significant when I didn't include the control, right? So there's no difference, as you can see, between ACR, ABX, and ABX, ACR, excuse me, right? But they are different from the control. And so, yeah, so basically these 3 blue tufts of lines all have the same slope. But if I'd shown the control, they'd be different from that, okay? So that's cool. And kind of the same thing here with like this atop those BACA. Well, actually, so the ACR and the control are different, but then the ABX and the ACR are different. And then the ABX ACR is different from the ACR. So this, where my crosshairs are, is different from this, and this is different from this, right? So it'd be nice to have like line segments over the top to indicate that those are significantly different from each other. Okay, so that's where I'm going, okay? So we have our statistical data now, and we're going to want to incorporate that statistical data. We've already done it with like comparing the differences, but let's go ahead and see if we can't make this look a bit more attractive in our plot. And so again, our plot has the control I added back in. So let's remove the control, and I think I'll do that after my inner join. So let's do filter treatment not equal to CTRL. Oh, and I forgot a pipe there. Okay, so that goes back to not having the CTRL. So before I worry about putting on those line segments, let's go ahead and try to make this look a bit more attractive. And so the first thing I want to do is clean up that x-axis because we converted it to be numeric rather than to be character, right? So let's see. Let's come in here and we'll do scale x continuous. And we'll do breaks equals. And so the breaks we have are 2, 3, and 4, right? So let's do 2:4. And then the values is going to be D, let's see. Yeah, I'm thinking levels, D $, treatment. So don't, yeah, it's not going to work because we're missing that 1 there, right? So maybe I will do -1 to get rid of the 1. Oh, this should be labels, sorry, not values. And so let me remove this and see if that worked. No, okay. So if I do the -1 on a vector, it removes the minus value, right? And so now what we can see is that we have those names in there. And I'm going to resist turning those 90 degrees for as long as possible. So we'll hold on. And then the y-axis we have from 0 to 0.6. I would prefer to show those as percentages. So what I'll do then is scale y continuous. And we'll do breaks. I'll do seek. So they go up to like 0.6. So maybe I'll do like 0 to 0.6 by 0.2. And my labels, I'm going to multiply by 100. So we'll do seek 0 to 60 by 20. And so now what you can see on the y-axis is that we have those percentages, right? So let's play with the labels a little bit. So we'll do labs, x equals null, y equals relative abundance. And I'll say that that is %. Yep, and I think I forgot a plus sign. I heard someone yell, thank you. And there we go. Cool. All right. Let's see. Okay. So everything is big. The text is all big. And so I want to reduce the font size. And the smallest font I'm going to want to use is a 6-point font. And so I think the text in the strip, I could see making that 6-point. So let me go ahead first and do theme classic, which oftentimes cleans a lot of stuff up for me. And so the theme classic puts a box around those strips, but it gives you like solid axis lines. It also gives you black text, whereas theme gray gives you like all the other stuff that we just saw with the previous version. Okay, so let's go ahead in here and we'll do theme, and I'll do strip.text element text, and we'll do size equals 6. And so that gets those to be smaller. Let's go ahead and remove the border. I'm going to do strip.background equals element blank. So that border is defined by the background, right? And so if we do blank, we'll get rid of the background. And so now we have that cleared up. You'll notice there's some clipping, right? Like this O is kind of missing something. We could go ahead and do strip.clip equals off. And so now we've got the full word, but we still see some of these things running into each other. And so this would be like, again, if we can get rid of some stuff, it'd be really nice. If we go back, oh, where did we have that? Here in the facet wrap. Let's do end call equals 5. Something like that. Yeah, so that's like 5 wide and 4 deep, but we have this like extra thing. I'm going to remove the others, I think, because again, to me, it doesn't really make any sense because it's like the pooling of a bunch of things. So let's go ahead and remove the others. I'm fine with doing that. And so we'll also do filter family not equal to others. And then that gets us space so that we can more or less see the full names, right? Cool. All right. Well, let's go ahead and shrink some of this other text. And I like putting the axis stuff at the top. So we'll do axis.text equals element text. Let's do size equals 7. Axis.title element text size equals 8. And I've got an extra space over here. Looking like that. And okay, let's make the lines a bit thinner. And so let's go ahead and do axis.line equals element line. We'll do line width equals 0.2, and then axis.ticks equals element line line width equals 0.2. I like to have my ticks and my axis lines be the same thickness. And so that's pretty nice. One thing I'm noticing on these labels is that like this ABX plus ACR is running into the ACR. So let's go ahead and put a line break after that plus sign. And so where did I define that? So we've got these levels up here in treatment, right? And I think what I'll do is I will copy that and paste it down, and I'll do labels, right? So we can change the label. So I could put like a \n here after the plus sign before the ACR. So let's go ahead and rerun that. And so now what we've got is that ABX plus ACR. Okay. Cool. All right. So this is coming together. All right. So I still need to put in those significant bars. Something that confuses me, distracts me, I don't know, is the names, trying to remember what panel each name goes with, right? So if I see this like Peptostreptococcaceae here, for whatever reason, my eye moves up to this data. But that's not it. The Peptostreptococcaceae is down here. Another thing is that oftentimes, well, it's kind of hard to see what's at 0, how far things are off of 0, right? Like, so are these at 0? Are they above 0? What's going on? And so I'm wondering if there's a way to change this panel. And what I'm thinking is I would like to draw a box around each panel that includes the name. And so I think that's what I'm going to do. So I think I'm going to draw a box for each panel that encompasses the name of the family. And then that way, we'll also get a baseline, right? We'll get like an x-axis, so to speak, for each of these to see how far they are up off of 0. The other thing I see Mark suggested was plot lines could be reduced as well. I agree. Let me do that real quick. Thanks for that suggestion. So we'll do line width. I'm going to do 0.3. Kind of like having the lines be a little bit thicker than the axis lines. And so that reduces some of that noise as well. Okay, so let's go ahead and make a border. And so we can do panel.background. And so as it says here, let me remove my face. Oh, let me see if I can get back. The background of the plotting area drawn underneath the plot. Okay. So let's do plot background element rect, and we'll do color equals black for the border. The fill would be like the interior. And so there we go. We now have that border. Let's go ahead and reduce the line width, or just set it. Do line width equals 0.2. And that looks pretty nice. One thing I noticed though is that like the left side where there's the y-axis is a little bit thicker than everything else. So I'm going to come up here, actually on all of them. I think I'm going to make axis line element blank. So we don't have, there we go. So we don't have kind of extra line on the y-axis and the x-axis, right? Cool. All right. So the next thing I want to do is bring those labels inside the plot. And we're currently leveraging the strip text, but I think what I'd rather do is maybe use like geom text to put the name inside the plot. Ooh, is there a strip placement inside? Okay, I will give this a try. Yeah, that, maybe I'll say strip position. Let's see. Strip. Oh, I've got to do this. Sorry. Within facet wrap. I'm looking at the comment. Sorry. I do stuff like this where I'm trying to do funny things with the y-axis. So I'm curious to see if this works, and it doesn't. I think like the strip placement inside is like if I had done what? If I did strip position bottom, then what you see is that the strip position goes in the bottom, but it's like inside of the axis, right? Whereas if I did like outside, then that puts it outside the axis, right? But that's not what I want to do here. I want it inside the plotting window. And so I'm going to put this back. Thanks for that suggestion, though. It's always, I like playing with facets like this. So what I'm going to do is I'm going to increase the span on the y-axis, maybe to go up to, let's go up to like 80. But I'm not going to show the 80, right? And so let's come back up here to scale y continuous, and I'll do limits equals c0 to 80. I did 80, but again, it's actually 0.8. The labels are multiplied by 100. Okay, so there we go. So now you can see we've got a little bit of white space up at the top. And let's then go ahead and move our strip text inside. And I'm going to, like I said, I'm going to use geom text. So let's do geom text. And then we're going to do we're going to do x is going to be 3 because this position is position 3, right? The ABX. And then the y, let's make it 75. And then the label is going to be family. Let's see. I think we also need to change the size. So we'll do size equals 6, size.unit equals pt. And it's upset. X.label needs to be a vector, not a function. Oh, okay. So this needs to be within an AES statement, okay? All right, so we'll do AES, label equals family, then all that stuff. There we go. Now the error goes away. But nothing happened. And I wonder if that is because I put it at y. Again, it's 0.75. There we go. Now we have that in there. But I see a couple things. So first of all, it's coloring it by something. Oh, I know what it's doing. And then it's actually, it looks kind of pixelated if you look closely. And that's because like this oscillosporaceae, it's putting it down, I guess probably 24 times, right? So one for each mouse. And so it starts getting a bit pixelated. And then it's putting in, the color we see is the last color that it put, right? So like this like Peptostreptococcaceae is gray because the last thing it did was put down one of these ABX plus ACR mice. So we're going to want to come back up here to our label family. And let's do unique on that. It's unhappy. Okay. So I think what we'll do is add data equals D, and we're going to filter that, or we're going to distinct that by family. And again, what that would look like would be this, right? So basically it's going to give us a table with 21 rows. And so we're going to insert a new data frame here. This AES is mapping equals that. So this should work. No. Oh, it's complaining because color not found. But what I could do, and so it's saying color not found because I don't have a color column in the output of this, right? So what I want to do though is maybe say color equals black to make it clear that I want the text to be black. And treatment not found. And so I don't have a treatment, right? And so the other thing I can do, because I don't want to, I could make up a treatment value, but that doesn't make sense. What we could do is inherit.aes equals false. And so what geom text is trying to do here is it's looking up here through these different aesthetics or columns that I'm mapping to aesthetics and saying like, well, there's probably no relabund column, although that doesn't matter because I set a Y, but there's no mouse, there's no treatment, right? All these things. But if I say inherit AES equals false, then that means don't inherit the AES statement from ggplot when I'm running geom text. And so as we can see now, the error message goes away. We now have those column, the family names in here. We also have our good friend others back. But we can now see that we've got our text in here, it's black, and it's not getting duplicated many, many times. So let's come back up and let's see. It's this family not equals others is kind of a pain. And so what we could also do is I'm going to go ahead and copy this filter into here to remove the others. And so now that others is gone, I can get rid of the strip text by doing element blank. And so that goes away, right? Okay, so I can go ahead and get rid of this strip clip off and get rid of this element text to clean things up a bit. Also get rid of that. All right, so I think that box really helps to pull in the family name. That's my opinion, right? You could argue that it's maybe a little busy to have that box around things, but I think it's cool. I'm going to roll with that. The problem, though, that we still see is that some of these names, like this Aries substreptococcaceae and the Peptostreptococcaceae, they kind of run across the plotting window, across the box, right? And so I don't want to shrink the font because it's already at 6, which is pretty small. But maybe what we could do is reduce the spacing around the panels. So let's go ahead and do panel.spacing. And we'll do unit. Let's try like 1 point to make it really narrow. And so that does that. And so I think that's like enough separation between the panels that you can see they're distinct panels. But we still have this problem with this really long name. There's a margin around the panel that we can also perhaps remove. So let's go ahead and do plot.margin. And we'll do margin. Let's do 2 all the way around. And that helped a bit. But like it's still kind of touching both sides, which is really annoying. What happens if we go to 0, or if we do 1 on the left and right? It's a little bit better. What happens if we make the spacing 0? So then that works, I think. I don't know what I think of that. I would like to have some separation, but yeah. I'm not totally sold on that. I think I want to take that back to 1 to have some separation. If we make our axis title 7, what happens if our text goes to 6? So I think that's probably about as well as I'm going to be able to do. I guess, yeah, I'm going to leave that there. Like they're pretty close to the border, but I'm not going to worry about that so much. So, all right. So again, I think that is looking pretty good. There's maybe some other things we could do with like the margin on our y-axis text. Okay, this is the last thing I'll try. So let's do axis.text.y element text margin equals margin. And then on the right, let's make that 1. So that pulls that in a little bit. You could also like shrink the ticks. So we could do like axis.ticks.length.y equals unit 3pt. Okay, maybe it's 3 by default. Let's make it 2. Pulls that in a little bit. I don't know. I mean, we're talking about like pixel widths of separations. I think that's cool. Again, we're trying to fit a ton of information into a small space. And the original, as you'll recall, was 2 inches tall. So if I take this back down to 2, it looks like that, which really isn't horrible, right? Maybe I wouldn't use all these values on the y-axis, but I think that looks, that's okay. Maybe what if we split the difference to 3? Something like that. I don't know. I'm going to take it back up to 4 because we're not done yet, right? We need to add those significant bars, okay? And to do that, again, we had our DD, and we're going to add in segments. So I'm going to come back up here and do like geom segment, and data is going to be DD, and then mapping is going to be AES, and we're going to have like, well, I'd like to do group 1 for like x equals group 1, x end equals group 2, and then y equals, I think I put my text at 0.75, so maybe at like 0. Something, right? And we're going to want to do inherit.aes equals false, right? And then our, yeah, and probably like line width equals 0.3, maybe. But there's some information in here we don't have yet, right? Like we don't have the x end, or the y. And that's because, again, we have a, We have a continuous x-axis. And so I need to turn group 1 and group 2 into factors. And I also need to come up with a y position, because we're going to have 3 lines, right? So we're going to have a line between ACR and ABX, ACR and ABX plus ACR, and then a line between ABX to ABX plus ACR. Okay. So let's come back up to DD, and I'm going to go ahead and do a mutate on group 1 to be a factor, group 1. And then our levels is going, well, you know what? I'm going to grab, I had it up here, right? I'm going to go ahead and grab this because we also changed the labels on that treatment factor. So we'll do that. And too many parentheses here. Okay. And then we need to do the same thing for group 2. let's see what this looks like. Okay, so now we've got group 1 and group 2, but we also have NAs. And I wonder if that's because, let me look here. If I've already got that line break. I already have that line break. All right. So, right. So what I called labels actually want to be levels. And so there we go. Okay. So now if we look at DD, we've got the right labels. And for now, let's go ahead and do y equals 0.73. And then let's see, y is going to be y. Okay, so again, now group 1 is a factor, but we probably want that to be as numeric. All right. So we'll pipe that to as.numeric. And then this will pipe to as.numeric. And so again, if we look at DD, we should get these numeric values. So those are like the x-axis positions, right? And then we've got our y. And so now when we run this, what we see is that we've got a line at 0.73. And we also have our control in here as well, right? It's starting at 1. So if we come back to DD, let's go ahead and do a filter group 1 equals 1 or group 2 equals 1 to remove that. Not equal to 1 in group 1 or in group 2. That didn't work. Why? Let's look. DD. Oh, I think it's supposed to be and, not or. Okay. Yeah, because if group 1, I don't want rows where group 1 or group 2 are 1. So I want both of them to not be 1. All right. There we go. So we now have that line. It's at 0.73. That's clearly too high. So let's come up here and we're going to do a better job of defining y. So we'll do case when. So case when group 1, and let's look at DD to kind of see what the combinations are. And so we've got, okay, so we've got 3, 2, 4, 2, 4, 3. Those are the 3 combinations, right? So case 1, group 1 equals 3, or sorry, I'm thinking, let's do the long one first. 4, and group 2 equals 2. Then let's make that 0.7. When group 1 equals 3, and group 2 equals 2. Let's make that like 0.67. We'll adjust these, right? And then group 1 equals 4, and group 2 equals 3. Let's make that 0.63 or 4. Okay. So that should work. And then otherwise, true, make that 0. Okay. Because those trues are going to be like group 1 equals 1 or group 2 equals 1, right? And so there we go. We now have those significance lines. Of course, we still have this other here. So I think those lines can probably come down a smidge, right? Like, I'm mostly worried about this like Enterobacteriaceae here, that we're kind of running into that. Let's get rid of that other first. And so again, back up here in geome segment, we can do filter DD, and then do family not equal to others. And this needs a comma. There we go. Okay. So again, I think those lines are either too high or our text is too low, or both. Let's try dropping them a smidge. So again, we did that up here. Let's go down just like one notch, 6461. So that comes down. So like, I think that works. The place where it doesn't quite, I mean, like, I think that works fine. The challenge is that for some of these, the lines are really high compared to the data, right? And so, like, I could see trying to put the lines down closer to the data where possible, right? I don't know. I'm not totally worried about that. I could see also maybe moving the title up a little bit. So let's see. Let's try moving the title up. So we've got, let's see, 0.75. So if we go up to like 0.77, and then our scale Y continuous goes up to 0.8. So let's try that. So that moves that up a bit. I don't know, I think that's pretty good. Let's see. Okay. John says, could you facet 4x5 rather than 5x4? Let's try that. It would be nice to be able to highlight the panels in which they say that in the text are particularly important. Okay. That's an idea. As we are changing the plot completely, are we constrained by the original size, or do we size to produce the best aesthetic look? I am not constraining myself by size. So again, if I go back to 2, so which would be the size of the original, we'd get that. Let's see. Do I still have that here? Let me get the original. For some reason, oh, there it goes. Okay. Let's see what this looks like. Right, so like these are the same aspect ratio, right? And I think even at 2 inches tall, mine is better. If I had to constrain to the same height, then I would probably shrink these labels down another notch. Because then we have the problem of like running into the top, right? But I don't feel the need to constrain, because again, like in the original, there's like below panel F are these panels, and these panels are really tall. I think they're trying to match the height of that panel. Like they're trying to keep things on a grid pretty well, which is fine. But there's also like space up here. I would like totally be refactoring D, E, F, G. I'd be refactoring all these, right? So I'd basically blow everything up and start over. So I think there's space to play with. This figure also doesn't take up a full sheet of paper, like the full page on a PDF. So I think there's room to be taller. I don't know. But I think even at the same aspect ratio as theirs, we could make this work by fiddling with some things. But I'm gonna put it back to 4 inches and be happy with that. So you'd ask, do you want to add the p-value? I don't. We have, in this plot, there are 20 taxa, and there's 60 p-values just for looking at what I've colored, right? So like this panel has 3 here, 3 here, 3 here, right? Up here, there's 3 p-values. So for each panel, there are 6 p-values. And so there's 20 panels. So that would be 120 p-values that we'd be trying to put on this chart. That's just like too busy. I don't think that's necessary. What I would do if they require like a precise or an actual p-value would be to have a table in the supplemental data that's like, here are your p-values. If you want p-values, there you go. I don't feel the need to put p-values on the lines or above the things that we have here. I just don't think that's necessary. Let's see. So what do the horizontal lines have to tell me below the name? So these horizontal lines tell us that for like Akkermansia, actually, you know what? Thank you for asking that. Yes, thank you for asking that. Because they don't tell us anything at this point, because I have drawn all of the horizontal lines. What I need to do is to also do a filter where the p-value, the PWP value, is significant, right? So if we look at this, we have that PWP value, right? And so if I'm curious, if I do filter p.crossgoal greater than 0.05, does anything show up? So like the Riken LACA shows up, right? And so what I would do then would be to say that the P cross goal has to be significant and the PPW has to be significant to get a line, right? And so if we come in here and do and filter P dot cross goal less than 0.05 and P dot PW less than 0.05. Oh, and I misspelled filter. All right, try that again. Good. Now we have meaningful lines, right? And so what this is telling us is that so I want to do some checking on that. But what this is telling us is that there's no difference in the slopes of the change in Akkermansia. There's no difference in the change in Akkermansia across the 3 treatment groups. So there is a change in Akkermansia because of the acarbose, the antibiotics, and their combination. But the amount of change due to those 3 different treatments does not differ, right? Whereas like with the Bacteroideaceae, there's no before-after change due to ACR or antibiotics. But there is a change for antibiotics plus acarbose, and that change is significantly different to acarbose alone or antibiotics alone, right? And I guess what we also find then is like for Lactobacilliaceae that there is a before-after change due to acarbose and acarbose plus antibiotics, but not a before-after change for the antibiotics. But there's not a significant difference between these 3 different groups. And so that's what the horizontal line is there to say. Does that make sense? But thanks for asking about that. That seemed weird. So there was a question about that I liked. Mike said, would be nice to highlight the panels in which they say the text are particularly important. So the one they're really interested in this paper is the Bacteroideaceae. And so you can think of a few ways to highlight that. And yeah, I'm thinking of how to do that. So one would be to change the text to be a different color. So first of all, one would be to sort these by what you think is important, right? Like these are alphabetically sorted. They're not sorted by anything else. And so I could totally see, and you would do that with like a factor, but I don't know why I would sort one over the other. You could perhaps do it by like average relative abundance in the control mice or something like that. Or you could do it by things that you think are most important. In this paper, they wanted to say that a carbose was working against anaphylaxis in a microbiota dependent fashion. So maybe you would do something like, you know, the ones that change the most with antibiotics and acarbose, you put first. So there's a way to like, you could sort these, right? So that's one option. The other option of like, if there's things that you think are cool, like this Bacteroideaceae, you could then, you could like change the text, right? So something we might do would be, so I do this on D for distinct. So if I came back up to D, I could make, let's see, I could make highlight. And I could then do if else family equals Bacteroideaceae. So if that's that, then let's make this like, let's see. I could do black. And if it's not, then let's make it gray. Okay. And it's upset. Oh, because I need 2 equal sign. I've done that twice in this episode. All right. And so then down here in geom text, right, I could add in here like color equals highlight. And then I could get rid of this color equals black. Oh, did I not run that? Where'd it go? D should have highlight. So it's got highlight. It's my text. Oh, because I've got that. Okay, so let's do family comma highlight. And yeah, okay. That's a little bit messy. And then highlight. Oh, because I misspelled it. All right, bear with me. We're getting to the end here. Highlight. So you do something like that, right? I don't know. Like if you really wanted to focus people on the Bacteroideaceae, you could do this, or you could obviously pick other colors, right? And it seems weird to have like 19 things be gray and 1 thing be black, but like I think in the paper they did mention like 5 or 6 things they wanted to like call your attention to, and so you could probably do that somehow, right? I'm gonna go ahead and turn that off, but that would be one way to do it, by changing the color of the text. Let me just rerun everything. Get back to that. So we could change the order. We could change the color of the text label. Another thought that like came to me would be to change the border color. And I'm not really sure how to do that. So that's like an interesting question here, right? So we have like this color black. So I'm curious if I do like C red, black. I think it should like alternate the colors. Nope, it just made them all red. All right. So that doesn't work. Another thought I would have, get rid of that. All right, let's try this again. Okay, run that, run that. Okay, we're back to black. So if I wanted to like make Bacteroideaceae have like a red border, I think I could do annotate, and then let's do, we're going to do layout equals 3 for this third panel, right? And then we'll do geom equals polygon. And I think you need like x, x end, y, y end. And I think what we could do would be like 0.5, or actually this is 2, right? So it's gonna be 1.5. And then this is going to be like 4.5. And then y would be, I'm going to put 0, but it's not really 0. And then the y max value was 0.8, I believe. Yeah, 0.8. So we do 0.8. And then we could do like color equals red. All right. It's been a long time since I've used Geom Polygon. Let's see what it wants for its aesthetics. I think I have to give it the XY positions. Yeah, so X is like a vector of values. Yeah, okay. So let's try X equals, so we'll go, I think like that. And then y 0 to 0 to 0.8 to 0.8. So that gets us that, but it's got a black fill. So let's do fill equals NA, gets us that. And so what is also happening is that we've got the expansion on, right? So let's see, if we did chord Cartesian, and then I did like y lim equals c 0, 0.8, x lim equals c 1.5 to 3.5, and then we can do like expand equals false, clip equals off, get that off, and get rid of this limits here on scale y continuous. I think I screwed up my limits. Yeah, it should be 4.5. Right. Something like that. Right, so like, and maybe you don't pick red. So the other thing I noticed, so like my 0 would need some help there, right? So maybe I make this like negative 0.02. Pull that up off, right? And then, oh, I can't help myself. Let's pull down the text a little bit to say 0.76, something like that. So that'd be another way to highlight it. Although I see that I've got to fix that bottom. I can't help it. So this is, what did I set that at? Negative 0.01? 0.02, okay. Let's see, so negative 0.02, negative 0.02. So you can do that, right? So that would like highlight the Bacteroideaceae. I don't know. All right, so some questions here. Yeah, so GG highlights things, and yeah, thanks for that. So that, yeah, that's basically what's happening under the hood if you're looking at how to highlight that. But if you didn't want that, we could also comment this out And I guess I didn't run it. Okay, it's like that. So I'm pretty happy with that. Again, the one thing that still gives me a little bit of pause is like the vertical position of those lines. And I could see trying to like drop them to be just above the end of the line. And maybe if you don't mind sticking around for 10 minutes, I'm going to try that. And if you have to take off, I totally understand. So this is in DD is where we're getting the information and where we're setting the Y position, right? And so if I come back to DD, what I'd be interested in is like, what is the maximum value that I get, right? And so I've got like the median change, but let's maybe get, let's get max equals max of dot x, or yeah, we're gonna do a map double dot x equals data, and we'll do max dot x $ after and dot x $ before. Okay, and so then if we look at this, we have a column. I think I forgot a parenthesis. Okay, that is going to be the maximum value of the before and after. Okay, and let's see. Oh, I put this in P. That's not where I want it. Sorry. I want this in DD, right here. Okay. And I'm going to put it with this mutate. And now let's see what we get from this. Sorry. And that's probably because I got rid of it up there. Okay, so let's try again. And so I will then get, I'll do max equals max of after and before. I think that needs to be within a C, yeah. And then we'll do dot by equals, and I'm going to do it by family. And close that parenthesis. And so now, oh, what did you do to me? Max equals max before, after, by family. Maybe I don't need those quotes. Uncultured. What is it doing? Let's see, if I look at this, I've got before, after. Yeah, it's upset. Okay, I'm going to go back to my other strategy of using map. So let's do mutate max equals map on thinking here. Let's see. Well, there's no reason I have to get rid of before and after, right? So I'll go ahead and do after and before. Okay. And then we're nesting within family. And so then in here, I'll do max equals max on, I have to say map, right? Map. And we'll do data, and we'll do max dot x $ after dot x $ before. And this is going to have to be in a C vector, C function statement. And I close that out. And this should be a map double. Sorry, I'm getting tired. All the mistakes coming here at the end. All right. Oh, dot x not found. What do you mean? Oh, because I need the tilde. More mistakes. Well, more practice for you all to spot my mistakes, right? All right, so there we have the max value for each family. And just to double check that that checks out, 0.177 for Acromantia is probably right there. For Bacteroid ACA, 0.446 is like right there. Okay, cool. And so then we also want to select the max here. And then we also want to select the max here. And then let's run this. And then we see that we've got our max. So for the Y, what I could see doing is taking the max, like let's make this max plus 0.03. And then this 0.6 and this 0.9. So basically I'm adding a value above the maximum value for each of those. Like that. So I don't know what you think of that. This, again, puts the lines closer to the data and is interesting. Yeah. I don't know. Let me know what you think. Do you prefer this approach or the other approach where everything was kind of at a fixed position on the y-axis? And yeah, I don't know. That's a way to look at it. Anyway, let me see here. So again, we have my version and their version, right? And so if they use the same width, mine is twice the height as theirs. And we showed that we can kind of perhaps play a little bit with the height to get different appearance. But I hope that your take home from this is that my version is far easier to interpret than theirs. Even a basic thing like putting the before and after control, the before and after ACR, and so forth next to each other would have been vastly superior to what they did. Because again, to compare like the ABX column, I have to compare it to this column over here. And that's hard, right? Stacked bar plots have all sorts of problems, including, as we see here, 21 different colors, which doesn't make any, that's just like too much, right? That we have like 2 different whites. And I think in the paper, they actually talked about bifidobacteria and Peptostreptococcaceae. And the other thing then is like these rectangles represent an average of 8 mice. Whereas here, I'm showing all 8 mice. You might not be able to see the individual mice very well, but the data are here, right? And you can kind of see the general movement. You can see the kind of variation in the data, right? Like there's a fair amount of variation in the Akkermansia in the before samples, but they all kind of like focus down in the after samples, right? But that's not something you're getting from their stacked bar plot, all right? Well, let me know what you think of this. I appreciate people sticking with this through to the end. I think this was a lot of fun. Whenever I see a stacked bar plot, I think, how could I do it better? How could I do it not as a stacked bar plot? I think putting a box around it, coloring by the direction and significance, getting those lines in to indicate significance, I think those are all fun little quirks. I really appreciated the question of like, how would we go about highlighting one thing over another? I thought that was fantastic. I really appreciated that question. And again, I would think about filtering, right? Like removing the panels we're not interested in, ordering the panels in terms of order of interest instead of alphabetical. And then perhaps if there's a few things you're interested in, either changing the color or the type of font in for the family name, or perhaps drawing a box around a different colored box, right? Basically around the panel. Those would all be things that I would think about trying to do, but I would certainly also be trying to think about removing some of these taxa that probably aren't super important, right? So things like this Reichenelaceae, low abundance, doesn't change a whole lot, probably not relevant. This uncultured, I'd love to know what that actually is. It changes under acarbose, but not the other conditions, it goes up with acarbose, but down with the others to flat. that's interesting. So anyway, those would just be some thoughts on the whole. Hopefully you enjoyed this. I will have a couple other videos coming out this week. One looking at how I would transform their this jitter plot showing Shannon diversity in the upper right corner here, panel D, and another looking at a redoing of panel E, this ordination. And again, my point in this week's set of episodes is to really emphasize the value of leveraging your experimental design to help your data visualization, right? This was a paired study. They had the same 8 mice sampled before and after each of the 4 treatments. So connect those dots, right? Connect those mice to each other so that we can more easily see the change. Also, use that pairing in your statistical analysis, right? Like they did not do that up here in panel D. They did not do a paired t-test or Wilcoxon test or anything. And that ultimately is causing this difference between control and ACR to turn up as not being significant. And to kind of give you a spoiler, it's just as significant as these other differences. So anyway, I will stop there. Really appreciate you all spending time with me on your Wednesday morning. Keep practicing with these ideas, thinking about how you can apply them to your own data. And I will see you next time for another episode